Our next topic is linear regression analysis, a tool for prediction. A prediction is a statement of what is believed will happen in the future based on past experience or prior observation. Marketing managers are constantly faced with the need to make predictions. The marketing manager has to worry about competitors' reactions, changes in sales, wasted resources, and whether profitability objectives will be achieved. Making accurate predictions is a vital part of the marketing manager's workday world. Linear regression is a predictive model, which uses relationships among variables to make a prediction. Regression analysis is concerned with the nature and degree of association between variables and does not imply or assume any causality. With predictive modeling, prediction relies on an observed relationship believed to exist between the factor you are predicting and some condition you judge to influence the factor. All predictions should be judged as to their goodness or accuracy. The goodness of a prediction is based on an examination of the residuals, also referred to as errors, when you compare the predictions to actual values. When you compare how far the predicted values are from the actual or observed values, you are performing analysis of residuals. Stated differently, assessment of the goodness of a prediction requires you to compare the pattern of errors in the predictions to the actual data. Analysis of residuals underlies all assessments of the accuracy of a forecasting method. So once you come up with your predictive model, such as by using linear regression, you apply it to the observed data, and then you examine the residuals to assess the model's predictive accuracy. Again, the examination of residuals consists of comparing the predicted values to the actual observed values. Regression analysis is a predictive analysis technique in which one or more variables are used to predict the level of another by using the straight line formula y equals a plus bx. We will examine what this formula means in just a moment. First, we will examine bivariate regression analysis, which is the simplest form of regression involving only two variables, x and y. Multivariate analysis is a more complex form of regression analysis in which there are multiple predictor variables. Regression analysis is a powerful and flexible procedure for analyzing associative relationships between a metric-dependent variable and one or more independent variables. It can be used to determine whether the independent variable explains a significant variation in the dependent variable. In other words, is there a relationship between the independent and dependent variable? It can be used to determine how much of the variation in the dependent variable can be explained by the independent variable. In other words, what is the strength of the relationship between the independent and dependent variable? It can examine the structure or form of the relationship, the mathematical equation relating the independent and dependent variables. And lastly, it can predict the values of the dependent variable. Bivariate regression analysis is a type of regression in which only two variables are used in the predictive model. One variable is termed the dependent variable, y. The other is termed the independent variable, or x. The independent variable is used to predict the dependent variable, and it is the x in the regression formula. With bivariate analysis, the straight line equation is y equals a plus bx, where once again y is the dependent variable, x is the independent variable. A represents the intercept, the point on the y-axis that the line cuts when x equals 0, and b is the slope, the change in the line for each 1 unit change in x. Regression is directly related to correlation, so we would think of the slope, b, as how much change in y, the dependent variable, is produced with 1 unit of change in x, the independent variable. Recall that in correlation we could have a positive association or a negative association. The same thing applies with linear regression analysis. Although bivariate regression is similar in many ways to determining the simple correlation between two variables, an equation has to be derived, as you can see on the screen. So one variable has to be identified as the dependent variable and the other as the independent variable, whereas in correlation, this doesn't matter. The examples given earlier in the context of simple correlation can be translated into the regression context. Can variation in sales be explained in terms of variation in advertising expenditures? What is the structure and form of this relationship, and can it be modeled mathematically by an equation describing a straight line? Can the variation in market share be accounted for by the size of the sales force? Are consumers' perceptions of quality determined by their perceptions of price? With linear regression analysis, we are estimating population parameters using our sample statistics. The population parameters are beta sub 0 and beta sub 1. However, these are often unknown and are thus estimated from the sample observations using the following equation, where y sub I hat is the estimated or predicted value of the population y, and A and B are sample estimators of beta sub 0 and beta sub 1. B is a constant and is usually referred to as the non-standardized regression coefficient. It is the slope of the regression line, and it indicates the expected change in y when x is changed by 1 unit. Again, y could mean sales, and x could refer to advertising expenditures. For example, 1 unit change in advertising expenditures might be $1,000 of additional expenditures, and that would be used to predict whether sales would increase or decrease. The formulas for calculating A and B are simple. The slope, B, may be computed in terms of the covariance between x and y. We covered this concept of covariance when we discussed correlation. As the equation shows, B equals the ratio of the covariance of variables x and y divided by the variance of x. This is how the covariance of x and y are calculated, and this is how the variance of x is calculated. And the simplified formula is shown here. The intercept A may then be calculated using this formula. A equals y bar minus b times x bar. Y bar is the mean for the variable y, the dependent variable, and x bar is the mean of the independent variable. The hypotheses that are tested by the statistical significance of the linear relationship between x and y are very similar to the hypotheses put forth in correlation analysis. The null hypothesis is that the population beta, or the population slope, equals 0. This means there's no association between the dependent and independent variable. And the alternative hypothesis is that the population beta, or slope, does not equal 0, which means there is a relationship between the independent and dependent variable. The test statistic of the linear relationship between x and y is a t-statistic with n minus 2 degrees of freedom, and it is calculated as the ratio of the slope divided by the standard error of the slope. This denotes the standard deviation of the population slope. Just as with analysis of variance and correlation, the test of association between two variables with linear regression involves partitioning the variation or the variance. The total variation in the dependent variable, which is the sum of squares of y, or SSY, may be decomposed into the variation accounted for by the regression line, which is SSRE sub REG, or sum of squares regression, and the variation due to the error or the residual variation, which is SS residual, or SS sub res. Below we see the formulas for calculating each of these. A related inference involves determining the strength and significance of the association between y and x. The strength of association is measured by the coefficient of determination, r squared. In bivariate regression, r squared is the square of the simple correlation coefficient obtained by correlating the two variables. The coefficient r squared varies between 0 and 1. It signifies the proportion of the total variation in y that is accounted for by the variation in x. We see the calculation for r squared on the screen. It equals the sum of squares due to the regression divided by the sum of squares due to y. This is further decomposed as we divide up the variance of the regression into the sum of square due to y, the dependent variable, minus the sum of squares residuals, and then that is divided by the sum of squares due to y. Rather than hand calculating all of these statistics, we will use SPSS to conduct bivariate regression analysis. You see the steps listed here. Select Analyze from the SPSS menu bar, click Regression and then Linear, and then we will move Attitude into the dependent box and move Duration into the independent box. We'll click Enter, and then we'll click on Statistics and check Estimates under Regression Coefficients, check Model Fit, click Continue, and click OK. Now for a demonstration. This SPSS demonstration uses the data from Chapter 17, in which a researcher wants to explain attitudes towards a respondent's city of residence in terms of durations of residence in the city. The attitude is measured on an 11-point scale, where the range is from 1, which equals do not like the city, to 11, which equals very much like the city, and the duration of residence is measured in terms of the number of years the respondent has lived in the city. First, we select Analyze from the SPSS menu bar. Then we click Regression and then Linear. Move Attitude into the dependent box. Move Duration into the independent box. Select Enter in the method box. Click on Statistics and check Estimates under Regression Coefficients and click Model Fit and click Continue. Then click OK. On the screen here we see the SPSS output that results from the demonstration that we just conducted. Now if we examine this output, we will see the model summary first. The model summary contains an important piece of information, which is the R square. Now remember that the R square tells us the percentage of variation in y that is due to the independent variable x. We also want to look at the ANOVA table, which tells us whether the independent variable had a significant effect on the dependent variable. And then the coefficient table more directly tests whether the slope is significant. So we can see that the slope b is 0.59. It has a positive sign, so that means there's a positive relationship between the two variables. Here's the t-statistic, and the significance level, or the p-value, is 0.000. We compare that to our alpha level or significance level of 0.05, and because it is less than 0.05, we can reject the null hypothesis with a 95% degree of confidence, and we can state that there is an association, in this case a positive association, between attitude toward the city and duration of residence. The R-square tells us that approximately 88% of the variance in attitude is accounted for by duration of residence. This is a strong association. Now that you're familiar with bivariate regression analysis, you're ready to step up to a higher level, multiple regression analysis. You will find that all of the concepts in bivariate regression apply to multiple regression, except you will be working with more than one independent variable. Multiple regression involves a single dependent variable and two or more independent variables. The questions raised in the context of bivariate regression can also be answered via multiple regression by considering additional independent variables. For instance, can variation in sales be explained in terms of variation in advertising expenditures, prices, and level of distribution? In this figure, you can see that purchases, intention to purchase, and preferences are in the center, meaning that they are the dependent variables. The surrounding concepts are possible independent variables. That is, any one could be used to predict any of the dependent variables. For example, one's intentions to purchase an expensive automobile like a Lexus could depend on one's income. It could also depend on friends' recommendations, word of mouth, one's opinion about how a Lexus would enhance one's self-image, or experiences riding in or driving a Lexus. In truth, consumers' preferences, intentions, and actions are potentially influenced by a great number of factors. For example, there are probably a dozen different demographic variables, there could be a dozen of lifestyle dimensions, and a person is exposed to a great many types of advertising media every day. Of course, in the problem definition stage, the researcher and manager decide on a manageable number of independent variables to be included in the questionnaire. That is, they have the general model structure in mind, but they identify and measure specific variables that pertain to the problem at hand. Because bivariate regression analysis treats only dependent-independent pairs, it would take a great many bivariate regression analyses to account for possible relevant dependent to independent pairs of variables in a general model such as the figure you see on screen. Fortunately, there's no need to perform a great many bivariate regressions, as there is a much better tool called multiple regression analysis. The general form of the multiple regression model is shown here. This refers to population parameters. This model is estimated using the sample by the following equation. As before, y is the dependent or predicted variable, x refers to the independent variable. However, now we have more than one, therefore we designate it with an x sub I, which will replace with the number of the independent variable. A is the intercept, b sub I is the slope for each independent variable, and m equals the number of independent variables in the equation. The difference now is that the b's, or the betas, are now the partial regression coefficients. This test involves a least squares criterion that estimates the parameters in such a way as to minimize the total error, which is the sum of squares of the residuals. This process also maximizes the correlation between the actual values of y and the predicted values of y. All the assumptions made in bivariate regression also apply in multiple regression. Because multiple regression analysis involves a test of multiple regression lines, to accommodate those multiple regression lines, a regression plane is used instead of a single line. Multiple regression analysis operates on an independence assumption, meaning that the independent variables must be statistically independent and uncorrelated with one another. Testing for the significance of the betas, or the partial regression coefficients, can be done in a manner similar to the bivariate case by using t-tests. The significance of each partial coefficient associated with each independent variable may be tested by the following equation. The t-statistic equals the ratio between the slope and the standard error of the slope. The t-statistic has a t-distribution with n minus k minus 1 degrees of freedom. You would use that information in addition to the significance level of alpha equals 0.05 to look up the critical t-value. Now for an example of multiple regression. Suppose that we wish to predict customers' intentions to purchase a Lexus automobile. So we perform a survey that includes an attitude toward Lexus variable, an attitude toward their current car variable, and an income variable. Here is the model that is going to be tested in this multiple regression. Y equals A plus the slope of independent variable 1 plus the slope of independent variable 2 plus the slope of independent variable 3. Here's the result. Our dependent variable, intention to purchase a Lexus, equals the intercept A, which is 2, plus 1 times attitude toward Lexus, plus minus 0.5 times attitude towards the current auto, plus 1 times their income level. This multiple regression equation means that we can predict a consumer's intention to buy a Lexus if you know 3 variables: attitude toward Lexus, attitude toward their current car, and their income level using a scale with 10 income grades. Here's how we would calculate a particular customer's Lexus purchase intention using the multiple regression equation. Knowing their response to the scale items for attitude toward Lexus, attitude toward their current car, and income, we multiply times the beta value for each independent variable, and we add the intercept, and that gives us the overall intention to purchase a Lexus, in this case a 9.5. Using the same dataset example from Chapter 17 that predicts attitude toward the city based on duration of residence and importance given to weather, I will conduct a multiple regression analysis to illustrate the concepts I've just discussed. First, we'll click Analyze, and then Regression, and then Linear. The dependent variable is still attitude, independent variable duration, and now we'll add importance to make this a multiple regression analysis. Selected for us is estimates and model fit. We leave that as is, and we click OK. The output we see here gives us the R-square, and we're going to look at the adjusted R-square. The adjusted R-square is adjusted for the fact that there are multiple independent variables predicting the dependent variable. And then the coefficients table shows us which coefficients significantly predict attitude toward the city. And we can see that both variables, duration and importance, have a p-value of less than 0.05, hence both are statistically significant. So we would conclude that both duration of residence and importance attached to weather significantly predict attitude toward the city, and that these variables explain 93.3% of the variance in the dependent variable.